Hello everyone. In the previous videos on adaptive control, I mentioned several times that your error can converge to zero, tracking error, and the parameter estimations can converge to the actual parameter values. But for the second convergence, we mentioned a condition called persistently exciting. So the R, this R that the system, the model, right? Because if you are doing MRAC, we are doing model reference adaptive control. The R that is the input to the model. If this R has enough variations in it, like harmonic or any other thing that is not just like constant, and it is, we say, persistently exciting, then not only E goes to zero, the error, also these estimations of the parameters, they should also go to zero. So AR tilde, for instance, for the first order system goes to zero, linear first order system, and a Y hat tilde goes to zero. And if you don't know what I'm talking about, please watch my previous video on MRAS, MRAC, MIT rule, and you'll see that this is the error dynamics equation for what? For a first order linear system in model reference control, where E is the difference between Y and Y of M. Y is the output of the system, YM is the output of the model, and we want this error to go to zero. And the model dynamics was Y dot equals negative AP times Y plus BP times U. And the model dynamics is Y dot M equals negative AM times YM plus BM times R. And the control law that we picked, U, was AR times R, and this is, there is a hat, plus a Y times Y. And these AR and AY are related to these unknown parameters of the system, AP and BP, through these two formulas that I have provided for you in the Simulink, you can see. So when we don't know AP and BP, we don't know the controller parameters. So the goal was to estimate these parameters of the controller, which indirectly means estimating the parameters of the system, and we picked these two parameter estimation laws, and we said that if and only if this R is persistently exciting, then these two will also go to zero. The E does go to zero regardless, but these two, they need a condition. And so I want to explain this persistently exciting with a little bit more mathematical definition, okay? Because it's easy to say persistently exciting, but what does it really mean? For us engineers, we have to define it mathematically. So, what does it mean? Let's take a look. In equation 1, E is, as I said, the tracking error. And as I said, if we pick the control law that I showed you, then we showed with the Lyapunov function that the E is guaranteed to go to zero. Okay, so ultimately E goes to zero, so this term and this term go to zero, which means now this term has to be zero. But the fact that this linear combination of AR tilde and AY tilde is zero does not mean each one of them is zero, because this is one equation between these two variables, and there is no reason that they're both zero. Especially that R and Y here are functions of t. They are time variable coefficients. Okay, so there is no necessity that they are both zero. And you might say, how come? I'll show you. So in order to see that better, I'm gonna combine this R and Y of t into this vector V of t. And let me use bold font, so it's a vector. And the two error parameters, parameter estimation errors, AR tilde and AY tilde, I call them vector A tilde. So then this left-hand side can be written as V transpose A tilde equals zero. Yes? Good? Now, let's see look back at the adaptation laws that we had for the first order LTI system, these were the adaptation laws. Now, as I said, as time goes on, the error goes to 0. When error goes to 0, that means AR dot and AY dot hat should both be 0, which means the AR hat and AY hat should converge to constant values. They are not changing anymore because their derivatives are 0. Since the tildes were the hats minus the actual ones, and the actual ones are constant, and remember we said that the hat ones also going to be constant, that means the tildes are also going to be constant too when time goes to infinity, ideally. So the error in parameter estimations also, they're both going to be what? Constants. Now, let's look at the special case that we always said this is not persistently exciting. What was the case? The case was when the R, the input to the model, was a constant like R naught. So we want to do a set point, right? We have a set point and we want the output of the system Y to basically converge to that. We can show that if R is a constant like R naught, then Y and Ym, which are the same thing, right, over time, they will converge to what? They will converge to, over time, they will converge to alpha times R naught, where alpha is the DC gain of what? The system, okay? That's the DC gain of the system for that physical first order system. Remember, Y dot was negative A Y plus B times U. As you know, in this case, the Laplace transfer function is what? If you want Y over U of S, it is going to be basically B over S plus A, right? So Y is going to be B times U over S plus A, and in this case, the Y steady state, as you know, per final value theorem, is the limit of S times Y of S as S goes to 0. And if you plug in, and let's say U of S is just what? U of S is just R naught over S, right? Constant. So if you plug in R naught over S here, that S with that S would cancel. The DC gain of the system is B over A times R naught. So it's just going to be B over A R naught. You see, so this B over A, you can call it that alpha that you can see here. And so Y goes to alpha R naught. R is R naught, okay? So if you plug them into this top equation, you get AR tilde R naught plus AY tilde alpha R naught equals 0. If you get rid of the R naught, which is a constant, you get this relation. And what is this relation? This relation is a linear relation between these two error terms that are constant with a slope of alpha. So if you plot it in the space of AR tilde and AY tilde, this is simply what? This is simply a line with the slope of negative alpha. So it is going to be something like this. Okay? And your final point could be anywhere on this line. It's not necessarily at origin where both terms are 0. It could be anywhere. So if you give the system a constant input R, the model, your final values for the parameter errors could be anywhere on this line. And if it's anywhere other than origin, that means they are not going to be equal to 0. So you will never converge. Your hats will never converge to the actual ones. You see that? Yeah? But if this R is not constant, then the first term and the second term are not going to be a linear multiple of each other. So the only solution for it is basically the fact that both of them are 0. Okay? Yeah, for instance, if it's a sine function, if you pass to this system a sine function, so this U is basically 1 over, let's say, S squared plus 1, then you'll see that you'll get different things, okay? Because y is not going to converge to a constant, and r is not going to be constant, and they are not going to be correlated with the constant, with the slope. So as I said, the only solution will be both of them 0. Now here, this is the part that I want to give you a mathematical description of persistently exciting. So we say r of t is persistently exciting if for any time t there exists a strictly positive constant t and alpha 1 both bigger than 0 such that the integral from t to t plus capital T of VV transpose dt is bigger than alpha 1 times I, and here this I is the identity matrix. Okay? So this is the mathematical definition for this system of what? Of persistently exciting, where V is, as I said, this vector here, R and Y. So what does it mean? VV transpose. V, remember, is R and Y, right? We transpose. And here, if we want to write it that way, we have to write this V as a column vector. So it has to be really like this. See if I can change it. Yeah, there we go. So it has to be like that. So we can say V transpose A tilde is, and A tilde also, it has to be a column vector as well. Let's see. So you write it like this. And if that's the case, then VV transpose is going to be a matrix. What matrix? In this case, if I want to show you, it is going to be basically R and Y times R and Y. So it is going to be R squared, right? And then RY, and then YR, which is the same as RY, and then Y squared. So the integral of this from t to t plus t dt should be bigger than or equal alpha 1 times I. So it should be alpha 1, 0, 0, alpha 1. If R is such that this integral is valid, then we can call it what? Persistently exciting. But if R is constant and Y is constant, what is the integral of R squared? Let's just focus on this 1 element from t to t plus capital T dt. And we remember we said R is R naught. So this is just going to be a constant R naught squared, the difference between them. So it's going to be R squared naught times T. Okay? This is bigger than or equal what? Alpha 1. Yes? And then similar things for the other ones too. For instance, for Ry, remember R is like R naught, and this guy is alpha times R naught dt. So it's just going to be alpha R naught squared t bigger than or equal 0. The other one is similar, and then finally integral from t to t plus capital T of y squared dt. This is going to be alpha squared R naught squared t. This should be bigger than or equal alpha 1. So you get conditions like that if it's constant. Can you provide all of that? And the answer might be not necessarily, okay? Because this alpha is not under your control, okay? That is the DC gain of the system. And remember, we said that, let's go back and look. For any t, there are strictly positive constant T1 and alpha such that this condition is true. So if I give you a specific R naught, if I give you this, could you find me such a thing? These two conditions, you might say, yes, I can. And you give me 1T and alpha. And then here, if you look, that's very similar to that, except it's multiplied by alpha squared. Okay, so if you compare this one and that one, right? First of all, alpha has to be zero, alpha has to be positive, T has to be positive, but T is positive. Alpha, the DC gain is positive, and remember DC gain was what? If you go back and look, the DC gain was B over A, right? It is B over A, and there is no guarantee that B over A is positive in this case because the system has to be stable. A is positive, but B, no, not necessarily. B can be negative if you want. So there is no necessity here for this guy to be positive. So this one forces my B to be positive, which is not necessarily true for every system. And if you compare the first one and the last one also, you can see that they are both bigger than alpha 1. There is no relation between them, so it does not really specifically specify anything about alpha. Okay, yeah. So in this case, alpha could be 1, could be bigger than 1, less than 1. So it kind of leaves you up in the air and not exactly giving you any condition. But if instead you had a sine function or some variable function, it was much easier to accommodate these conditions. Okay, yeah. So if this condition is true, then I can show you that the only solution when this condition is true, the only solution for the A tilde is 0 only. Why? Where does that come from? All I need is to go to relation 2, which is this relation here, this one, pre-multiply both sides of it by V, and then integrate them. Well, this side is 0, this side is VV transpose A tilde dt, and you integrate it from T to T plus capital T. If this A tilde is constant, as we said it is, and bring it out of the integral, it becomes A tilde times the whole integral equals 0. Remember this, A tilde can come out of the integral. But this integral, if you look at it, that is this guy. And this integral is bigger than or equal alpha times 1. So in general, it could be bigger than or equal some positive number. And here, when this product of this integral times A tilde is 0 and the integral is positive, then the A tilde should be 0, as I said. Now, for a first order linear system, we can interpret this. There is more math, but I don't want to get into it. There is more math, and you can show that for a first order LTI system, this condition 3 is equivalent to what? To saying that R should have at least one harmonic in it. If you have one harmonic in R, then you should definitely get what? Get A tilde to also go to 0. To show you that, I go back to the same example that I did last time, but I added this manual switch so you can switch between a harmonic and a constant. And when we do harmonic per last time, you can see that not only the tracking error goes to 0, but also if you look at a hat R and a Y hat, you can see that they are converging to the values that were supposed from them from this formula. Based on the numbers we had for AM, BM, and AP, BP, clearly if you calculate AR and AY, you can see that the actual numbers are what? For AR is 1.5, for AY is half. And you can see that these hats, these estimates of them are converging to 1.5 and 0.5. So in this case, your error in estimating the parameters AP and BP are going to 0. Yes? But if I switch that to a constant input, double click here and run it, and R here is just constant 1, you can see that again the tracking error goes to 0. Look here, the system settles at the desired value, but look here, if you see, instead of settling at 0.1 and 1.5, 0.5 and 1.5, you see that if you zoom in, your AR hat does not settle at 1.5. Actually, it does settle at about 1.785. Let me just write it down. So in this case, R naught was 1. AR hat is converging to what? 1.785, and a Y hat is going to just zoom in. It is almost 0.12, so 0.121, let's say. So let's write it down, 0.121. Okay, yeah? What does it mean about a tilde? Remember that a R should be 1.5 and a Y should be 0.5. So what does it mean about the tildes? Let's calculate the tildes. AR tilde is AR hat minus AR, and AY tilde is similar, AY hat minus AY. So what do we get? If you subtract these two, you get negative 0.285, and for this one, if you subtract, you get negative 379, correct? Now, what's the ratio between these two? If we calculate it, so we want to know, remember we said that in the linear case, a R hat plus a Y hat times alpha is equal to 0, AR tilde, sorry, plus alpha AY tilde equals 0. So here we can find alpha if we plug in these numbers, right? So alpha is clearly negative AR tilde over AY tilde. And if I plug those numbers, I will get, let's type it in, you get negative 0.752. Now look at this magnitude, 0.752, and I want you to look at something else here. So I want you to look at here on how much the Y is converging to. Remember, R naught is 1, and alpha times R naught is your final value that you converge to. So alpha is the ratio between final Y and final R. And if you look here, what is this number that the Y is settling at, or YM is settling at? And you see that number is what? Look here. You look at this number, you see it's about 0.75 or 752 or something. And that is this guy. Do you see? The only thing that I made a mistake was this here. This AR tilde is positive, not negative. So this is going to be positive here. Positive 0.75, and as I just showed you, the DC gain, you can see that is 0.75 times 1, and 1 was this constant here in R naught. Okay, so hopefully you got an idea of what persistent excitation means. Now, this is the definition, and we said what it means for a first order system. For second order system, it is a little bit different, and for nonlinear systems is not a clear definition. So you cannot get something nice like this for a nonlinear system. For linear system, as I mentioned in one of my previous videos, that means that per unknown unknown that you have in the system, you need to have two harmonics, or two variable components, not just necessarily harmonics. Okay, and so you might wonder, if I change this 1 to something else, would that make any difference? So if I just replace this with, I don't know, a ramp function, if I bring a ramp function, would that count, right? Would that give me zero tracking error? So let's just run it as the last part before I finish this video. So first of all, you can see that clearly your system is tracking the desired from the model. And if you look here, you can see that not really. You're not converging to 1.5 and 0.5, okay? But having that one harmonic did the job for you. So you need to have some harmonic in the signal. Okay, hopefully it was useful to you. I'll see you in the next video.